Thank you so much. First of all, I would like to thank all the organizers for giving me this opportunity to speak in front of all of you. So today I'll be speaking on the defect characterization in gallium nitride semiconductors. Gallium nitride semiconductors or GaN semiconductors in comparison to, I think my video is not on, I guess. So, so in comparison to silicon, it's not so popular among the general public. But lately, there has been some devices appearing in the market that is attracting a lot of attention. For example, if you're saying rapid charging solution of your smartphones, some of them are thanks to GaN devices. Then if you have recently owned electric vehicles, then it will not be surprising to see GaN drivers or GaN devices down converting efficiently the power from high voltage batteries to the heating, ventilation, and air conditioning system of your automobile. And of course, there are many more applications within the vehicle. Then, as we already know about the white light emitting diodes, that has been here for a while, and we have almost accepted it in our daily life. Then it also goes beyond the civilian applications into the military domain, where GaN devices are being used for jamming signals, unwanted signals. So these materials are still suffering a lot from large amount of defects that are intrinsically present, and it's almost hard to get rid of them at the industrial scale without increasing the cost of production. And this is mainly because there are no substrates available for growing gallium nitride, and currently they are grown on foreign substrates such as sapphire, silicon carbide, and silicon. At imec, we are working mainly on the silicon 111 substrate, and one of the downfall of this is that it induces a lot of defects, for example, threading dislocations and stacking fault. So what you're seeing here is on the left side, is a 10 micrograph of a typical GaN-based buffer stack on silicon. This is something we need even before we can actually grow active device layers. So for example, here you have the silicon on the bottom, and then we start with a nucleation layer, and then we need a transition layers, or some people call it a strain management layers, which are typically step-graded AlGaN layers, starting from high concentration of aluminum content to low concentration of aluminum content AlGaN. After that, we grow an undoped gallium nitride, and it's only after this that we can actually grow active device layers. So as you have already noticed here in the 10 micrograph, that we are seeing these lines that are actually with high density appearing at the interface of aluminum nitride and silicon. So here they're appearing, these are threading dislocations. So here they are with a very high, they generate with a very high density. Sometimes it reaches 10 to 11 to 10 to 12 per centimeter square. But as they cross through these interfaces, their density starts to drop. Either they annihilate among themselves, or they bend, or they cancels out at the interfaces. And thankfully, by the end of the device layer, in our samples, we have something like 10 to the power 9 per centimeter square of threading dislocation density. Because GaN has or the most common form is vorticized hexagonal crystal structure. These threading dislocations can have two types of Burgers vector. One is C type, that is along the growth direction, and one is A, which is in plane. And of course, threading dislocations can also have both type of Burgers vector, so we call it A plus C type. So in most cases, the majority of the threading dislocations that are formed in GaN, they are either A type, they are A type and A plus C type, and there are very few pure C type threaded dislocations are seen. And this is the topic that I will be presenting here, that how we managed to study these threading dislocations and their electrical properties. So there are two ways to look at them. One is we can either go through the cross-section. We take a device structure, go into the cross-section and measure it there, or we can go from the plan view. But of course, then we need some dedicated structures, and these dislocation lines will look more like zero-dimensional defects. So these are the samples that I'll be quickly discussing. So here we am presenting 4 different samples. On the left, there are this is basically a PN diode. Not going too much into detail. The rest is just to grow the active device layers. The most important part is this PN diode, and among the 2, even more important is the drift layer, the yellow region. It is around this. This is the drift layer around which a high voltage has to be applied. So if we are talking about 100, 200, 500, 650 volt of applications, it is the drift layer that has to hold it without breakdown. So important detail to remember is that we are dealing with 2 different carrier concentration. One is in the order of 16, and the other is 1E17 per centimeter cube. This is all n-doped by silicon. And then we have 2 additional layers where we have a thicker drift layer. One is 3 micrometer and 5 micrometer with silicon doping in the order of 16 per centimeter cube. So how we do it is you can see the schematic from the cross section of our PN diode. We actually make the N+ contact from the top side. We etch down the entire stack, because it's impossible for us to make contact to the N+ layer from the back side. And then we have the P contact also from the top side. So that's why very often you will see I'm writing here SVT. That means semi-vertical transistor, because it's not really a pure vertical transistor, as we have all the contacts from the top. So from the top view, this is how our diode looks like. P-body contact here, and this is the drain contact. So we cleave through these diodes, and then we study the cross section by electrical SPM. So first, quickly wanted to go through scanning capacitance microscopy in case among the audience there's some who are not aware of this technique, as most of the time I'll be speaking on it. So in this case, we make use of metallic AFM tip to contact the sample, and as the tip hovers around, the local capacitance under the tip changes. And usually this change in the capacitance is recorded by the RF resonance capacitance sensor, which is basically a circuit comprising of capacitance and inductor, which will give a particular resonance characteristic. And as the tip sample capacitance changes, it adds to this resonance circuit, and thereby it changes its resonance characteristic. Usually this change is too small to be analyzed in its direct form, so we make use of the lock-in technique, and this allows us to look at the capacitance in the form of differential capacitance, DC-dV, which is actually a high frequency measurement, because this frequency of measurement is around a gigahertz. And at the end, we have the signal in the form of amplitude and phase, depending on how you want to see your signals as the lock-in outputs. So now the two outputs that we are getting, based on that, the amplitude is usually sensitive to the carrier concentration or doping concentration in the material, and also to the charges, local charges. Phase, on the other hand, gives us a binary information. It can tell us what is P-type region and what is N-type region. So if your lock-in conditions are same, then independent of the material being used, for example, GaN, silicon carbide, silicon, germanium, you will always have the same phase values for a particular type of doping. So first, we wanted to see what we are looking at to understand the contrast. So we start with the one of the stacks, silicon doping 16 order, 750 nanometer thickness of the drift layer. And this is the DC-dV phase. First, we confirmed that we can easily see P-type doping because it appears quite white here. And this is, if we look at the DC-dV phase profile, we always get phase of around 30 degrees there. And all the N-type regions, for example, N+, we have the drift layer, low doping, 316, and then N++ GaN. it appears at a 180-degree phase shift from the p-type region. And this confirms that DCDV phase is giving us the correct, is actually measuring correctly the type of the doping. And in the regions where we have no doping, for example, undoped gallium nitride and the transition layers, we actually see noise. It basically it fluctuates between 180 degree to plus 180 degree, but because we have averaged it around, we are seeing a different value. So now we can look at what we are seeing in the DCDV magnitude. So now here we have different contrast in different layers. For example, we can see the P, this is the DCDV profile. We have the P plus region. Within the N and the N plus, we have different values. Then there is some distinctions. For example, there's a drop and then a sudden rise forming a peak at the P plus N junction being seen here. And then there is also an increment in the DCDV between the N plus and the undoped gallium nitride. So this is, well, we are not going into this detail, but all of this magnitude can simply be explained by the dependency of the DCDV on the doping concentration, which is non-monotonous in nature. For example, this we are showing it for the p-type silicon calibration samples, which of course are available in imec as we produce it ourselves, and it's also commercially available for sale. And as you can see here, once the doping concentration goes down from 1E20 towards 1E16, we see an increment in the DCDV, which saturates around 1E16. But as we continue to lower down the doping concentration, furthermore, DCDV drops. And we think at this point where we do not know how much is the doping concentration, even with additional techniques like spreading resistance profiling, we believe if we just extrapolate it, we think we are able to look at 1E14 per centimeter cube of doping concentration. But of course, we need some other way to verify it. So we come back to the defect part. Now having seen what the signal looks like, when we look at a bigger picture of the area, we actually saw that in the drift layer, there is a non-homogeneous distribution of the DCDV. And actually, this is forming something like a funnel shape or elongated features extending along the bulk where DCDV actually drops down to zero, especially from the junction. So when we filtered out the topography a little bit more, we found that there was no hint of the topography variation similar to the DCDV distribution. This told us that this is something not related to the morphology. So we took the other sample where we have a higher doping concentration of 17. Here we found that in the drift layer, the distribution was more homogeneous. There was some local drops in it, but we can actually identify them in the morphology. So those are more related to the typical AFM artifacts. So at this point, one may wonder that, okay, this must be the optimal condition for high voltage application, like higher carrier concentration of 1E17. But the optimal criteria for high voltage application is that the drift layer has to be thicker and the doping concentration has to be lower. So we cannot use this kind of sample, even though they look quite well in DCDV maps. So to understand better, we went for a thicker samples. So this is for the case of 3 micrometer of drift layer. And actually, this is where we started to realize that we are dealing with threading dislocations, as until now, there was no report suggesting that DCDV maps can show threading dislocations in the cross section. So you can already see they're extending quite well from the junction down towards the N plus region. And actually, in some cases, you can also see that they're seen also in the N plus region. And so now we wanted to understand why we can see threading dislocations for lower carrier concentration, but not for higher concentration. So this can be understood from the work of Bagani and his colleagues who made a calculation of the space charge density around threading dislocations, which in case if they're acting as deep acceptors. And this was done for different doping concentration in the background, mainly N-type, going from 1E19 per centimeter cube to 1E16. So most of our 4E16 or 3E16 per centimeter falls somewhere here. So as you can see that the moment we go from 1E16 to 1E17, the dislocations are effectively screened by the by the background carrier concentration. So this is the reason why we were not able to see the space charge or the local DCDV drop around threading dislocations when the carrier density was 1E17. And of course, it will make it even harder if we try for much higher background carrier concentration. So we made a decade simulation of a PN diode using similar values for the parameters for the threading dislocations, but for a PN diode. And as you can see in the space charge map, we actually managed to obtain similar space charge distribution, which looks similar to the experimentally obtained DCDV contrast around dislocations. So now, now we have a hypothesis that we saw threading dislocations, signature of threading dislocations, but what's the proof that these are threading dislocations? And second, how do we prove that these are they are associated with deep acceptors? So for that, we actually carried out electron channeling contrast imaging. So ECI is also called ECI, and this is very sensitive to local distortion in the crystallography, typically given by local defects such as dislocations or stacking faults. So this is a very robust technique to look at them. So, but of course, it is also very important that we cannot work on surfaces that are very rough. So we had to polish the cross section. So we used a combination of mechanical and CMP. And actually now you can see that we are observing threading dislocations which are appearing with a white contrast extending from the P side towards the N plus. There is some damage happened here, but that is really not so important here. So now there is another qualitative way to distinguish if the dislocations or defects are acting as deep acceptors. So normally the deep acceptors we expect to be close to the mid gap. So usually if they act as non-radiative recombination centers, then we can claim with the CL analysis that they are located in the mid gap or they are deep acceptors. So this is how a typical CL map will look like. We are also seeing some regions where we have reduced recombination or let's say non-radiative recombination, which also extends from the P to the N plus. So here in the N plus, we have quite a high luminescence going around. So when we do a one-to-one mapping between ECI and CL, we actually find a very good correlation between the two. So these are from the same area. So what you can see is that all the threading dislocations that can be seen in ECI can be traced back to the CL map, and they appear as a darker contrast. But additionally, in the CL map, we are also seeing regions where we see non-radiative recombination paths that cannot be traced back to ECI. So this is more related to the fact that the two techniques have different information depth, much deeper for the CL technique. So now we wanted to see the correlation between all the possible threading dislocation that we can see in electron microscopy and our AFM analysis. So voila, you can see this is also done on the same area. So we actually get a perfect one-to-one correlation between local drop in DCDV and non-radiative recombination. So with no exceptions, we found that every single dislocations, A and A plus C type, they all are non-radiative recombination center, most likely related to their deep acceptor nature, and are associated with depletion region. So now we want to move towards the second way of looking at or studying dislocations. So of course we cannot do it if you're interested in on the PN diodes, if you're interested in the N-type gallium nitride drift layer. So here we stop the growth within the drift layer, and this is how a typical morphology looks like. What you're seeing here is a step terrace morphology with little dots. So these big dots are actually dislocations with C components. As I mentioned earlier, we are expecting more of A plus C than just C. So it will be safe to say that all of them are, most of them are A plus C type. They're slightly bigger in nature, and they usually terminate the step terraces. Then the second type of dislocations is pure A type. So they have in-plane Burgers vector A, and they're really small, and they do not interact with the step terraces. Sometimes it is not possible to see them because if the tip is extremely, if not sharp enough, we don't see it. Or if there's some contamination, even then we don't see it. Usually these A-type dislocations are formed at the low angle grain boundaries. So this is the DCDV map of the corresponding DC map of this morphology. As you can see, all the dislocations, A-type and A plus C-type, they all are associated with a drop in DCDV. What is worth mentioning is that on the pure A-type dislocations, the drop in DCDV is much wider. You will also notice that in most cases, the pure A-type dislocations are always arranged almost like a row, in a row. So it is easier to identify them if you don't have a good morphology. And we will have one of those examples later. So this again proves from this side that these both type of dislocations, we have depletion region. And now we had the opportunity to do DCDV spectroscopy on these dislocations. So in this case, we actually make a bias sweep from negative volt to positive volt, or the vice versa around. Or you can start with 0 as the Park tool allows. In this case, it's always a sample bias. So what we have done is we identified 2 A-type threading dislocations, and we carried out, this was based on morphology. First, we obtained some curves on an area where there were no threading dislocations. So that is a dislocation-free area, and this is the black curve that represents it. And then we took several of these curves on the two A-type threading dislocations, and as you can see, we see a shift in the DCDV curve, and we measured this to be around more than 1.5 volt. So this is again a qualitative proof of deep acceptors because of this high shift. But of course, we want to do a bit more quantitative, so we went TCAT simulation. So in the literature, we found there are 2 possible values that one can get for threading dislocations. They may also coexist together. So one was a shallow trap around 0.6 electron volt from the conduction band, and the other was a deep level around 2.5 electron volt from the conduction band. So what we did, we only varied trap density in the dislocation core. And what we found is that for the shallow traps, we do not get this 1.5 volt shift, irrespective of how much electron trap density I increase. But on the other hand, for a deeper one, that is the 2.5 electron volt, we see this shift of, we can easily obtain this shift of 1.5 volt for electron trap density between 0.25 and 0.5 traps per unit lattice. So now we can also see the same thing in the surface potential maps as expected. For the N-type semiconductor, if a defect is acting has a depletion region around it, which is going to be positive charge, it will result in an increase in the conduction band around, or we can say increase in the surface potential. And we actually obtain also here an increase in the minus ECPD this is minus E times CPD around both type of threading dislocations. Here it was difficult to know if it was severe more on the A type or more on the A plus C type because of the noise, background noise. So at last, everyone asked question, can we say something about the conductivity of threads? How bad are they, especially when they are being used for high voltage applications? Because that's how we define if a material can be used for high voltage applications by using a certain factor, that tells us about the breakdown voltage. So in this case, as I mentioned earlier, even in the absence of good morphology, we can know where the pure edge type dislocations is by looking at the pattern of the electrical signature. So here is the topography, and this is the current map obtained at minus 1.5 volt. So basically, this is a forward bias condition. In the reverse bias, we actually saw almost no current in anywhere. There was no contrast. So this is came out quite nicely that almost actually all threading dislocations, there was no conduction at all in their core. So this means these thread dislocations are actually non-conductive thanks to their deep acceptor nature. But this can be problematic for the light applications because they are still non-radiative recombination centers. So I hope I didn't go too fast or too slow. So in conclusion, we actually used a combination of techniques with different electrical modes of scanning probe microscopy, and combined with electron microscopy techniques to evaluate charge, conductivity, and recombination and their recombination properties. And we actually came up with one particular conclusive theory. So first, so both A and A plus C type threading dislocations in the drift layer, they are associated, and in the PN diodes, they are associated with the space charge region or depletion region. We confirmed with the surface potential mapping that there is a upper band bending going on. With the cathode luminescence, we could see that they do act as non-radiative recombination center that points towards their mid gap or deep acceptor levels. By combining both TCAT simulation and scanning capacitance microscopy analysis, we confirm that they are situated certainly below the mid gap. And at the end, these dislocations are certainly not going to play a big role when it comes to high voltage applications because they are incapable of conducting current through them. So at the end, all of this work, of course, cannot be done just by me. So we have this big team who are working on this topic on various different aspects. So I thank all of them. And I must acknowledge that we have this project has received funding from a couple of projects from the European Commission. And of course, I'm really grateful to the Prague systems because most of these measurements were carried out on their HiVac tool and the results came out extremely good. So thank you so much for listening, and this is open for discussion now.
Okay, thank you very much, Dr. Minj. Do we have any questions in-house here on this talk? While we're waiting for people to formulate the question, I have a quick one myself because the modeling for scanning capacitance on silicon devices is pretty well known. So we have a metal tip coming in contact with the silicon, which has a native oxide layer. We're making a MOS capacitor.
Yeah.
So this is not necessarily the case for 3.5 devices or for gallium nitride. So I wondered if you have any particularities in sample preparation that you have to do to image this.
So basically, so usually we don't consider, or at least I didn't consider native oxide layer during the calculations. It's not that we never did. We also considered gallium oxide, which can be present, but we didn't see a big impact in the simulation results. And I think the main reason is that the band gap of gallium oxide is actually similar or even lower than gallium nitride. So the band bending doesn't change similar to silicon or silicon dioxide interface. Then also one thing we know in gallium nitride is that the oxide layer is self-limiting, so it cannot grow beyond one monolayer. So so this is why we actually could avoid using gallium oxide native layer in calculations to prevent simulation time. For the sample preparation, usually for the measurements from the surface, it is really not so necessary, especially if these are freshly grown. But I think that you can still get rid of this one monolayer of native oxide by using this aqua edge, or I think that should work. For the cross section, we usually measured right after cleaving. So and
no polishing necessary.
So for the polishing case, also you don't need it because once you polish it, it actually removes. There's no oxide there.
Okay.
And then you can bring it after making the back contact. You can always bring it in the high vac system. So then we don't actually worry about the oxide formation there.
Okay, thank you.